Okay, today we're looking at section 2.2, which is going to be a more formal definition of a limit. And, well, actually, still not as formal as we could get in a few sections, but we're just going to look a little bit, not so much graphically, but more algebraically at a limit. So hopefully you guys got going on the course compass and on your online homework. And if you didn't, then I hope that you will get busy on that soon, because we do have homework due coming up. Okay, so we are in section 2.2. But before we do that, you might remember that at the end of 2.1, I had asked you to remember some factoring fun. So let's see how that went. Did anybody look up the difference of two cubes? And somebody's got a computer right there. You can probably Google it. All right, so it was, if you have a cubed minus b cubed, any of y'all? Did y'all remember how it factored? You want to tell me? Like this, and then it's a minus b, yeah. And then it's a squared plus just ab plus b squared. So if you FOIL that out, what happens is, you'll just get a cubed minus b cubed. Okay? Now, if it's the sum of two cubes, a cubed plus b cubed, all that changes is the signs. It looks very similar. You're going to have a plus b, and then you'll have a squared minus ab plus b squared. Okay? And then the other one that I asked you to factor was 6x squared minus 11x minus 35. And there are lots of techniques to factoring, but trial and error is one that works. And probably at this level, you guys are probably pretty good at trial and error. So meaning that the possibilities for 6 multiplying to get 6x squared would be 2x and 3x and 6x and 1x, right? So you just try, okay? And I happen to know the answer, so I'm going to try and win. But anyway, 2x and 3x does actually work. Now, your possibilities for negative 35 would be a negative 35 positive 1, or negative 1 positive 35, or negative 7 positive 5, or positive 5 negative 7, right? But you want to get negative 11. So in your head, you might, in order for it to multiply to be negative and then add to get negative, it's got to be 1 negative, 1 positive, and the larger, it turns out in this case, the larger product needs to be negative. So if I do the 35 and the 1, that's just not going to get me the 11x. So if I put a 7 here, that's going to make negative 21. And if I put a 5 here, that's going to get me positive 10, which will add to get the negative 11x. So familiar? Stare at it, play with it till you get it. Okay. All right. So now we are moving on to section 2.2. It says in the last section we looked at finding limits graphically and numerically. In this section we will look at additional methods for calculating limits, and they include factoring, rationalizing to create a common factor, and the Sandwich Theorem. So these are just little tricks of the trade for limits. And the best way to start any problem, remember, is plug it in, plug it in. You always want to start with that, because that may be all you have to do, and you're wasting your time if you're trying to do some snazzy algebra on it. So, for example, number 1 really is just a plug it in problem. We can just plug in this negative 3 in for x, and we'll get that this is equal to the limit as x approaches negative 3 of 5 minus negative 3 to the 4/3 power. 5 minus negative 3 is going to be 8, so this is the limit as x approaches negative 3 of 8 to the 4/3. I don't know, it's been a while, right? But to the 4/3 means the cube root of 8, and then you raise it to the 4th power. And fortunately, the cube root of 8 is a nice number. The cube root of 8 is 2, and then 2 to the 4th is 16. And you could do that with your graphing calculator. Raise it to the 4/3 power. Make sure you put it in parentheses, the exponent in parentheses. Everybody know that you can get these lecture notes online ahead of time, right? So you can go to the website and you can get them blank. So and then you can also get them filled in. So either way. Okay. Number 2, let's go ahead and try just plugging it in first. The limit as y approaches 2 of this is called a rational function. This is a linear function in the top and then a quadratic function in the bottom, just reminding you of some language. But so if I do the limit as y approaches 2 and I try to plug in, I'll have 2 plus 2 over 2 squared plus 5 times 2 plus 6. So this is the limit as y approaches 2 of 4 over 4 plus 10, which is 14, plus 6. So that's 20. So this is 1/5. Okay, let's try this next one, number 3. This is the limit as h approaches 0 of the square root of 3h plus 1 minus 1 all over h. Okay, if I do a direct plug-in, I'll get 3 times 0 plus 1 minus 1 over 0. Well, 3 times 0 is 0, so that's just going to be 1 under the radical, but the square root of 1 is 1, and 1 minus 1 is 0. So this is 0 over 0, okay, which I call yucky. Okay, and that it's yucky because you can't divide by 0. Remember, that's not defined. Now, there's yuckier things in the world, like 5. Well, I don't know if they're yuckier, but more complicated. 5 over 0 is actually more yucky than 0 over 0. 0 over 0 has a chance of actually having a limit if we do some algebra, if we play with it a little bit. So what we're going to do is play. If you had gotten 5 over 0, it's just going to be that it's one of those infinite, and the limit doesn't exist, like you were talking about last time with the asymptotes. Okay, so what we'll do is a little technique called multiplying by 1 in a mysterious form. Okay, so in a helpful form, we will multiply by 1. And in this case, for this problem, if we multiply by the conjugate of the numerator, what will happen is this radical will disappear a little bit and help us out. So we are going to multiply, so we will force a common factor by multiplying by the number 1 in a mysterious, I don't know if it's not that mysterious, but it's kind of, it seems strange, form. Here, it's going to be the conjugate of the numerator. You may remember this from rationalizing radical expressions in college algebra when you didn't want to have the radical in the denominator, so you would multiply top and bottom by, whatever it was. Okay, so the conjugate of the numerator is the square root of 3h plus 1 plus 1. That is my conjugate. Okay, so we will take this limit as h goes to 0 of the square root of 3h plus 1 minus 1 all over h, and we will multiply on the top and bottom by the conjugate. You can always multiply by 1. Right, which is what we're doing. It's just weird. I mean, 5 over 5, 7 over 7. Yes?
How is that the conjugate? How do you come up with plus 1?
Well, what you'll see is it's just kind of called the conjugate. I don't know if you remember when you looked at complex numbers, when you had like 5 plus 7i, and then you had 5 minus 7i. Those were kind of conjugate. It's like exactly the same, except one has a positive and one has a negative. And what happens in those is if you multiply 5 plus 7i times 5 minus 7i, when you multiply those out, the imaginary part falls out. And what's going to happen here when you multiply it in the numerator, you'll see that the radical will fall out. If I do the square root of 3h plus 1 times the square root of 3h plus 1, I'm just going to get 3h plus 1, right? If I FOIL right here. And then when I FOIL here with this one, see how those are going to cancel? And then I'm just going to get minus 1. So it's clever. It's like a clever thing because it gets rid of the radical. Now don't go crazy. Down here we can just leave this as this right here. There's no sense in distributing that h through, and you'll see why in just a second. Because what happens in my numerator here is my 1's cancel, right? And then I have 3h over h times this. Well, the h, because this is just 3h over h, those h's will cancel as well, okay? And so now I just have 3 over the square root of 3h plus 1 plus 1. Now I can try and do a direct plug-in and see if I get any better luck. So now if I look at the limit as h goes to 0 of 3 over the square root of 3h plus 1 plus 1. So I didn't do anything to the problem. I just changed its form by multiplying by 1. It's like I just, you know how like when you, if you're feeling bored, I don't know, this is kind of a girl thing to do, but if you're feeling bored with your furniture and you don't have any money, you can just move it all around and it feels like you have a whole new look in your house because you've moved your furniture. And have you ever done it? It feels weird. But it's really, nothing happened. It's just that you change things around. Yeah.
So radicals can be in the denominator.
Yeah, especially for what's going to happen right now, because now I'm going to do the direct plug-in, and I'll get 3 over the square root of 3 times 0 plus 1, or 3 over the square root of 1 plus 1, which is 2, 3 halves. Okay, so yeah, I mean, if you were reporting an answer, typically you don't have radicals in the denominator. That's actually sort of not as important as it used to be. That was back in the days before graphing calculator, or before calculators. A mathematician would understand approximately in their mind what the square root of 3 over 2 was, but 1 over the square root of 3, it was more challenging to compute in your head, and so that's why we always would have the radical in the numerator. But nowadays you kind of see it. You don't see it as much because you can just type it in your calculator, it doesn't matter. But in this case, we were using this technique to try and help us figure out what the limit is. Everybody okay? All right, so now let's look at another problem. See, now what do you think on this problem? Let's be careful first. Let's try a plug-in. If I put the 4 in, I'm going to get 4 minus 4 over 5 minus the square root of 4 squared plus 9. That's going to be 0 over 5 minus 16 plus 9 is 25. That's square root of 25 is 5. So I do get 0 over 0, which is yucky, but encouraging, because 0 over 0 implies that there must be some common factor that I can cancel out if I could just come up with it. So I will use the same technique that I used in the last example, except what do you think I will multiply top and bottom by on this one?
5 plus the square root.
Yeah. The conjugate here is going to be actually in the denominator. It's the denominator that I'm going to try and eliminate. So I will multiply top and bottom by 5 plus the square root of x squared plus 9. 5 plus the square root of x squared plus 9. Okay, and so I will do a little, this one might be a little bit more challenging. I'm still going to, just based on my suggestion from earlier, I'm still going to leave this part just in this form, even though it feels kind of like maybe I should multiply it out. The reason I didn't multiply it out is because I was really trying to eliminate the radical in the denominator. I wasn't messing with the numerator, so I'm just going to leave that like that. All right, now in the denominator, 5 times 5 is 25. notice when you multiply this times this and then that times that, the middle term falls out, and then you will get minus this squared, which will just be minus, careful here, x squared plus 9. Okay, and then let's clean up our denominator a little bit more. I'll have 4 minus x, and then this is 5 plus the square root of x squared plus 9. And then I'll have, I've got 25 minus x squared minus 9. So does everybody agree that that's 16 minus x squared? Feel okay? Okay, and then this 16 minus x squared is actually the difference of two squares. So I can factor that as 4 minus x times 4 plus x. Remember the difference of two squares, how that factors. Okay, and then what's the cool thing that happens? Well, hopefully we see that the 4 minus x's cancel. And now when I plug 4 in, I'm no longer going to get 0 in the denominator, am I? So now when I do the direct plug-in, I'm going to get 5 plus the square root of 4 squared plus 9 over 4 plus 4, which is, this is the square root of 25, which is 5, so this is 10 over 8, also known as 5 halves. Right? No, 5 fourths. Sorry. Okay? So that one was a little bit more complicated, but not too bad. All right? Let's look at number 5 then. Okay. When you do the direct plug-in, you should automatically kind of see the 0 in the denominator for x going to 2, but I'll do it here. It's going to be 4 minus 14 plus 10 all over 0, which, yeah, is 0 over 0, which is the yuck. So let's see if we can't clean this up. What do you think would be a good idea? Well, we're not going to use that technique anymore. But there is another little technique that we could do with the numerator. How could we change it? Yeah, I heard it. We can factor the numerator. So we can write this as, and see, if you're bad at factoring, you almost always know that x minus 2 is going to be one of your factors. I mean, you know the denominator. You're hoping the denominator is one of your factors, so at least you got one. Now you just have to guess at this one. But you'll put an x here, and you should be able to reason out that it's going to be, I think I have a typo on this problem. Wait, no. Yeah, -5. Sorry. I have a typo in my brain. Yeah, because it multiplies to be positive 10. So they both have to be negative. Okay, and so now you can cancel the x minus 2's, and we'll then be able to do a direct plug-in, which will just be 2 minus 5, which is -3. Good? Okay. Excellent. What happened to my this problem? Looks like it's got a cubic in there, so this will, or no, it's just not going to be the difference of 2 cubes. So it's just going to be, come on. Okay, so on number 6, you should see the 0 over 0 pretty quickly. Do y'all see that because you just plug in? So let's try factoring. What can we do with the numerator? Well, how about, could we factor a y squared out of there? Because y squared divides into both of those, right? And so if we divide 5y cubed by y squared, what will we have left right here? 5y plus, if we divide 8y squared by y squared, what do we have left? 8. Everybody okay? You can always check by distributing through here. Okay? Now here, I can factor out a y squared on this one as well, and I'll have 3y squared minus 16. My y squareds then will cancel. So I will cancel those. And now it does appear that a direct plug-in will be allowed. If I plug 0 in here, I'm going to get 8 over negative 16 or negative 1/2. Yes?
I'm having a problem seeing that as a 0 just like on the spot.
What you do is you plug 0 in wherever you see a y.
Oh,
So this will be
yeah, never mind.
5.
Never mind.
Are you okay? No, that's okay. It's good to ask questions because other people are probably in the same boat. Okay, number 7. Maybe if we do a direct plug-in, this will be 2 cubed minus 8 over 2 to the 4th minus 16. That's 8 minus 8 over 16 minus 16, which is 0 over 0, or yucky. So we will try a technique. Now, I kind of warmed you up on this one. It's a difference of 2 cubes, v cubed minus 8. You might remember 8 is 2 cubed, right? So we can write this as it was v minus 2 times v squared plus ab. So that was 8v plus, sorry, just kidding. So like this is v cubed minus 2 cubed. So if it's a minus b times a squared plus ab, so that's going to be 2v plus v squared, which is 4. Are y'all following me? That was that formula for the difference of 2 cubes. All right, what about the denominator? What is the denominator? It's actually the difference of 2 squares. You could write that as v squared minus 4 times v squared plus 4. Do y'all agree? And then this v squared minus 4 is again the difference of 2 squares, right? You can think of this as v minus 2 times v plus 2. So you have the limit as v approaches 2 of v minus 2 times v squared plus 2v plus 4 divided by v minus 2 times v plus 2 times v squared plus 4. So my v minus 2's cancel, and then I'll put the 2 in here. 2 squared is 4 plus, if I put, since it'll be 2 squared plus 2 times 2 plus 4. Now I'm just plugging in. And then I'll get 2 plus 2 times 2 squared plus 4. So this is 4, 8, 12 over, this is 4 times 8, which is 32. So 4 goes into each of these, and that'll be 3/8. Everybody happy? Doing okay? Not so far. All right, now this is just a little bit of just understanding limits. You can sort of use the distributive property on limits, okay? What feels right is probably right, okay? For example, on this one, you can think of this as the limit as x approaches 4 of g of x plus the limit as x approaches 4 of 3. Now, you were told in this problem that the limit as x approaches 4 of g of x is exactly -3. And so you can replace this entire expression with what it's equal to, which is -3, plus what is the limit as x approaches 4 of 3? I want to see. What is that asking? What does the limit ask? The limit asks, what is the y value as x approaches a particular number? In this case, our function is simple. It is the constant function 3. Y is always 3. It is y equals 3. So as x approaches 4, what is the y value? 3. It's just 3. Does that make sense? Do y'all see how easy that is? It's so easy it's hard. Okay? But yeah, your final limit here is the sum of these two, -3 plus 3, which is in fact 0. So that's where you're headed now.
All right, so that's the limit. Then what was, so y is just 3?
This limit is 3. If I asked you to limit as x approaches 7 of 12, it's just 12. Now, if it was the limit as x approaches 7 of 12x, it would be 84 because you would put 7 in for x. But your function there is so simple it's hard, right? But your function is y equals 3. It's not y equals 3x or y equals 3x squared or something that you would obviously plug it in. But it's just y equals 3, which is the constant function, which means for any x, you're always going to get a y value of 3. Now,
limit is y, or limit is y.
absolutely. Yeah.
Kind of like f of x.
Sort of. Yes. Yes.
So y isn't the function of x? G of x?
Well, yes, y is the g of x. Yeah, this is saying also what is g of x's value as x approaches 4. And you were given that it was -3.
So that limit, g of x is completely different from y?
No, it is the y. It's the function value.
Okay.
Y is the function
All
value.
right, that's why I'm just I'm confused. So then y equals 3, but the function g of x equals -3?
Yes. So a different y, a different function. We're two separate functions.
Okay.
We've got a function that equals -3 and a function. Well, and actually, this function, you don't know if this function is always -3. You only know that this function, this limit is -3 as x approaches 4. Whereas this expression, you know that it's always equal to 3. You could put any number you want in for x, you would always get 3.
Yeah.
Just if you just graph the y equals 3. Yeah, it's just a constant function. But g of x, you don't know what g of x is. So it could actually, if this were x approaches 7, we wouldn't have an answer to that problem because we don't know. We only know what it is as x approaches 4. But this one, x can approach to anything. I could change this to x approaches 12, and the answer would still be 3 because it's just a constant function. Okay, so let's try b now. It says what you can do here is you can actually just plug in. So you can say, you can think of this as the limit as x approaches 4 of 4 times f of x. And so I put 4 in for x. So this is going to be 4 times the limit as x approaches 4 of f of x. Well, we were told that the limit as x approaches 4 of f of x is 0. So I can replace this entire expression with 0. I get 4 times 0, which is 0. Okay? Now, on C, it says the limit as x approaches 4 of g of x quantity squared. Well, you want to think of that as the limit as x approaches 4 of g of x whole thing squared. Okay? We know what this limit is. We know that this limit is, we were told it's -3, and so we're going to square it, and we get 9. On this one, yeah, you can just put the limit into each piece. So we can write this as the limit as x approaches 4 of g of x over the limit as x approaches 4 of f of x minus the limit as x approaches 4 of 1. Well, what is the limit as x approaches 4 of g of x? What is the limit as x approaches 4 of f of x? What is the limit as x approaches 4 of 1? What did I hear? Did I hear? 1. It's just the y value. Are y'all with me?
Oh, okay.
Yeah, yeah. All right. -3 over -1, which is then 3. It's fine. It's all a process. You're doing good. Okay. It says evaluate the following limit for the function f of x equals x squared when x equals -2. Okay. All right. So let's do a little bit of work first. This may actually, you may remember this from a college algebra class. as I start working, you might recognize. Does anybody recognize f of x plus h minus f of x over h?
I recognize this one.
Yeah, it was called the difference quotient. Good. Yeah, it's called the difference quotient. You may remember that. But anyway, we have that f of x is equal to x squared. So I can replace f of x with x squared in this expression. But I need to determine what f of x plus h is. So I'm going to go ahead and find that first. Oh, actually, and they want it when x equals negative 2. Excuse me. So I'm going to go ahead and say f of negative 2 is going to be negative 2 squared, which is, of course, 4, right? So they want us to look at the limit as h goes to 0 of f of negative 2 plus h minus f of negative 2 all over h. Okay, so we already know what f of negative 2 is. We know that we're going to put a 4 in for this expression. We'd like to know what we put in for this. So we'll just say f of negative 2 plus h. Well, what that means is you're going to replace negative 2 plus h in for x in this expression. So you're going to put negative 2 plus h in for x here. So this is going to be negative 2 plus h squared. Everybody okay? Which is, if you FOIL this out, it's going to be 4 minus 4h plus h squared. Everybody okay?
Can we explain again why? Okay, so why did we plug in then?
Okay, so we started with what they gave us, right? And they asked us for when x equals negative 2 to evaluate this, and they told us what the function was. So I'm going to take negative 2 and I'm going to put it wherever I see an x. Okay, now I haven't done any work with a bunch of f ofs, and so I know I need to express this function entirely in terms of x's or h's. I don't want the f there. So f of negative 2, I know what that means. F of x is equal to x squared. So f of negative 2 will just be negative 2 quantity squared, which is 4. So that means that I will replace f of negative 2 with the number 4 in just a second. Okay? Now, I need to figure out what f of negative 2 plus h is. So what I'm going to do is this negative 2 plus h becomes like my x, right? So that's why I have negative 2 plus h quantity squared, okay? And so then that means what I'm going to do is I'm going to replace this entire expression with what it's equal to, which is 4 minus 4h plus h squared. You with me? So I'm going to take this, because this is equal to f of negative 2 plus h, I'm going to put it right here, so no more f's. And then I'm going to put, instead of f of negative 2, I'm going to put the answer, which is 4, right? And then I'm going to do a little bit more algebra. So I'm going to have the limit as h goes to 0. Instead of f of negative 2 plus h, I'm going to have 4 minus 4h plus h squared, and then minus 4 all over h. Now, you know you've done these correctly if everything that doesn't have an h in it cancels out in the numerator. So notice I have 4 minus 4, which goes away, and then I do just have h's left. So I can factor the h out of the numerator, and I'll have negative 4 plus h all over h. Now, remember, the whole idea of a limit is to plug it in. But if I plug it in at this moment, I have 0 over 0. But now I can cancel these h's because I factored it out. And now I do a plug in, and I get negative 4 plus 0, which is just negative 4. Okay? So eventually, you will learn this. The difference quotient actually comes from the slope, the formula for the slope. You remember you have x2 and x1 and y2 and y1, but you could do f of x2 and f of x1 and x2 minus x1. And if you were being really crazy, you could say that your x2 is only h away from your x1. So instead of expressing it as x2, you could call it x1 plus h. And because the one hurts to have to write all the time, you could just call it x. And so this could be x plus h, and this is x. And the distance that those 2 points are away is h. And remember, the whole idea is we want that h to go closer and closer to 0. I'll do this again. I'm just kind of familiarizing you with the language. So as this goes to 0, it's actually saying what is the slope at the instantaneous point x, in this case, x equals -2. So we have just determined that this parabola, and we'll go into this a lot more in a minute, but I'm just kind of, not a minute, in a couple days, but I'm just giving you a little teaser. It's a little appetizer. If this is f of x equals x squared, that's our friend, right? What this is saying is when x is -2, at the instant that x is -2, our slope, the slope of our tangent line, is exactly -4. And you can almost feel it, even with that kind of crummy drawing, it feels pretty steep. -4 is a pretty steep slope. Does that make sense? Sort of? Okay, good. All right, now we get to talk about the sandwich theorem. When I wrote this, I used to have different notes. I was using a different book, and I'm really into technology. Can you tell? And so it was when I was really fascinated by putting pictures into Word documents. That's how old I am. I thought that was really cool. And so I used to go out and get clip art, and I remember I had a big old hamburger. It was like, take a bite out of the sandwich theorem. Everything was really corny. That was my corny stage. I had a lot of clip art because I thought it was fun. All right, so the sandwich theorem, basically the idea of the sandwich theorem is that if you have a function and you don't know, maybe this works, if you have a function and you don't know the limit, if you could sandwich it in between two functions that you do know the limit, and these two functions had the same limit, then doesn't it make sense that the one that's sandwiched in between would also have that limit? That's the idea. So you sandwich it in between two functions that have the same limit that you know that your function is in between. Okay, so there's really three techniques that we looked at in this lesson today. We looked at the conjugate, which was like sort of an algebraic technique. We looked at the just factoring, which is another algebraic technique. And then this is the sandwich theorem, which is a little bit more sort of beautiful and creative, because what that tells you, and it's creative and beautiful and not going to be required at this level of mathematics too much other than for you to observe it and understand it. Meaning it's creative if you had to find a limit of a function and I didn't tell you to use the sandwich theorem, you would have to just sort of come up with two functions that you could sandwich it between, which takes a lot of experience that you may not have right now. But I think you can understand the idea of it, especially if I give you two functions to sandwich in between you feel good about. You know what I'm saying? So that's where we are on this one, because it's a sort of a creative endeavor. But, I mean, I'm sure you can be creative. Okay, what is the sandwich theorem? All right, we're going to suppose that we have a function g of x, and it's less than or equal to another function f of x, which is less than or equal to yet another function h of x. And we're going to use we're going to say for all x in some open interval containing C except possibly at x equals C. And so this has, your question at the beginning of class about with the open circle, that this is the scary math words of the open circle, except possibly at the instant C, right? This language right here is getting the open circle, but the interval is anywhere around it, except at that instant. So I know that this language is kind of funky. All right, if the limit as x approaches C of g of x is equal to the limit as x approaches C of f of x, and those are equal to some finite number L, okay, whatever it is. If you get the same limit for the g of x and for the h of x, then the limit as x approaches c of f of x, that's the meat, right? F is the meat, and g and, oops, did I say h and write f? This has to be an h. Okay, this is the bread. G of x and h of x are the bread, and f of x is the meat. But if g of x and h of x are both equal to L, then f of x also has to be equal to L because it's sandwiched in the middle there. So what they're saying visually, if you have some function that you don't know, say f of x, and you want to know its limit at a point C, if you can find a function that is above it and then closes in on a number, and we know the limit of that function, h of x, and then we have another one underneath it, and we know its limit is also that, then we can say that the limit of f of x is that as well. Okay? So let's look at our last example then. It says, use the sandwich theorem to find the limit as x approaches 0 of f of x. If we don't know what f of x is, but we know that it is sandwiched in between two functions, the square root of 5 minus 2x squared and the square root of 5 minus x squared. Okay? Well, this is actually pretty easy. Looks scary, but it's actually pretty easy because you can do direct plug-ins for, this is like your g of x, and this is like your h of x. So you can look at the limit as x goes to 0 of g of x with a direct plug-in, the limit as x goes to 0 of this square root of 5 minus 2x squared, which of course just plugging in is going to, oh, sorry, my hand hit that thing. Just, I have to get this to recalibrate. Come here. Just plugging in, we can do the square root of 5 minus 2 times 0 squared, right? Or just the square root of 5. And the same argument, if we look at the limit as x goes to 0 of h of x, that's just going to be the limit as x goes to 0 of the square root of 5 minus x squared, which is also the square root of 5. Okay? So these are both equal to some limit L. Yeah?
So when are you going to know the limit of h of x and the limit of g of x? How are you going to know that's this, like, is actually touching the limit of...
Well, you don't. All you know is that, and see, it's not, you don't, you know that around the interval they have the same value, and so it has to be true that at 0 it is sandwiched in between.
That's just that's what I'm asking. Is how do you come up with
The two.
without someone telling you f of x and h of x?
Yeah, g of x and h of x. Yeah, and like this example, I'm just sort of playing with the theorem, just trying to get you to see it. But we will look at some limits that you can't show algebraically that you have to use the sandwich theorem to prove. And it is just, you just try. I mean, you would just try them. But in my experience with the sandwich theorem, it's used to prove limits that have been proven for a long time. So that, you know, it's not, you're not going to have to really be creative and come up with your own. But somebody did, you know, somebody. And it's just getting very familiar with functions and messing around with functions. So you'll get there. All right, so what can we say by the sandwich theorem? The limit as x goes to 0 of f of x is? What will it have to be? Square root of 5. Yep, because your g of x and your h of x were. Okay? All right, so that's it for this lesson. We finished early. Sorry. Okay.